We can, for example, create a line MAT here, that is, a line material, drag it to Geo, then select material. Then, now we are gray, right? Let's turn it into a pure white. Let's talk about this color later. Let's see that this line actually has an attribute, right? Here its attribute, that is P, its position. Another one is called line width, which is the thickness of the line. Another one is called line color attribute, which is its color. So we can achieve some of our effects by controlling these three attributes, for example, these three attributes. Okay, let's look at it now. First of all, let's look at what these lines are like. They are all in a certain position. For example, if we look at a certain position here, it will automatically disappear, right? It looks a little stiff, so let's make something now. It can make our line thinner when it disappears. And it never gets thicker when it grows. Then when it is about to disappear, it will gradually become thinner. We can adjust the line width we just saw, right? First, in front of this noise, we press the right mouse button to create a math mix. This will be very, very common in our pop. Which means that it can make some algorithms and adjustments to these attributes. For example, we are going to tell you a piece of knowledge now. We just remember what effect we want to achieve. It is the process from the emergence to the end of our thread. That is, from its growth to its final extinction, its line is from thin to thick and then to thin at last. So what is the information we have to get in this place? Let's think about it first, right? We want to achieve this effect. First of all, I think the first point is every particle dot. We just mentioned the life cycle of each of our particles, right? Our particle, how long is it from birth to death, right? That is to say, when the particle is about to die, we make it thinner. When it is in the middle, we make it the thickest. When I was born, it was also thin. We can control the thickness of our line in this way, right? Then we know a parameter, which is the life length of each particle. What is the other value? That is to say, the current particle, because we are rendering in real time, right? To what extent is the current particle alive? So, for example, if we set this particle, it only lives for 3 seconds. If we pause the current particle now, how long is it alive? Maybe 2 seconds, maybe 1.5 seconds, right? So what we need now is to know these two pieces of information. In fact, we can roughly calculate and determine where our thickness is located. Okay, so that everyone can better understand this knowledge, let me draw something for you. For example, if we have a particle now, we first need to know two things about the particle we just mentioned. The first is the particle we set for how long it can only live, right? Actually, there is a professional term here called particle lifespan. It's our particle's life cycle. I need to write it down, called the total length of the particle's lifespan setting. So this is actually a fixed value, right? Because we have set it up. So what's the second one? How old is the current particle, right? It's called particle age, which is the age of a particle. We call the current length of particle life here, but this is not fixed, right? Then it's not a fixed value anymore. That's a value that changes over time. So for example, we set this particle, the total length of its life is 10 seconds. That is to say, from 0 to 10 seconds it disappears by the 10 second, and from the 0 second it appears. So at the beginning, the age of this particle was 0, right? But later on, for example, when we reach 5 seconds, does that mean this place is 5? Lifespan still won't change, okay? So let's use this to perform some calculations for us now. We come to combine here, where it can be combined with all the attributes we just mentioned. First of all, we choose operation. That is how we operate it. We see some of the attributes we saw earlier, and you see a lot of options, right? We can deal with the attributes we mentioned earlier in many ways. We choose a divided by b here. That is to say, what kind of thing do we want to get by removing a certain number from a certain number, right? Now let's use the particle we just mentioned. Partage can actually be found on the right here. Then what is divided by? Divided by part lifespan, that is to say, we need to use what we just saw to tell you. What do we have to divide this 0 by this 10? 0 divided by 10 still equal to 0, right? Splitting 0 into 10 parts is still 0, right? For example, in the next 5 seconds, right? It becomes 5, let's change another number, not 5, let's change it to 2. What is it when we use 2 divided by 10, which is the second, is 0.2. At this moment, it is 0.2. Well, let's give it a name at this time. The number we get, we call it particle normalize. Okay, what is normal? We've actually talked about it just now. Normal is the operation we are doing here, which is normal. That is to say, our numerical value is a value from 0 to 255, and we have turned it into a value from 0 to 1, which is called normal. That is to say, after performing this division here, we obtain a percentage equivalent to. What percentage of our particle's entire life cycle is it now, right? When our particle was first born, it was 0%. And then it lived for 2 seconds later, so now it's a 20% position in its life cycle, right? What we obtain through this method is the percentage of its life cycle. Then we proceed to the next step of the algorithm. Here, we change it to a -b and subtract 1 from the part normal life we just calculated. Then we get a new normal life, which means we go back to this algorithm and subtract it with 1. We get what? Using 1 to 0 still equals 1, right? For example, if we subtract 0.2 from 1, we get 0.8. That is to say, what we just got is a percentage of how long this particle has lived. So, if we subtract it from 1, it means there is still a percentage of how long it has lived. Okay, finally, let's add one more. Let's go change its name to this normal life. So now we have what we want, which is to say, where is our particle currently in its life cycle and how much is left, as we mentioned earlier. This is the normal life we have now, with the data of what percentage of the entire particle is left. So this data is a number ranging from approximately 0 to 1. Okay, then we have completed this algorithm now. Let's go and give it a new name. What can I do after changing my name? We will match this with the latest data we just obtained. Let's first think about how the number we obtained works. Let's not look at so many particles for now. We only consider one particle which has a number of 1 since birth, right? We just went through the algorithm just now. In the end, it obtained 1, which means that at the beginning its line width, that is, the thickest width of its line, was 1. Slowly moving upwards, gradually and continuously upwards, gradually this number, this 1, gradually becomes smaller and smaller. And it becomes a 10 divided by 10 is equal to 1, and then 1 minus 1 is equal to 0, right? That is to say, at the end of its life cycle, all of our lines will become invisible lines, right? Okay, now let's go to match the name. In fact, we don't need to change this place directly. We copy this name. In the result scope, the name of the number we got is line width. Let's take a closer look now. Is it true that our lines become very thin when they are at the top, and they are in a very thick state when they first come out? We don't let it operate. We see this as a state that we didn't adjust just now. When we turn it on, it is such a state, right? Okay, now that we have done it, how to control the thickness of our line? For example, I think the whole line is a little too thick now, right? What should we do? We can add 1 more. We do 1 more division and we divide the line width by 10. The whole is much smaller. Maybe 10 is too much. Let's divide by 2, make it only half as thick as before, and finally get the line width. In this way, we can also adjust the thickness of the line as a whole, right? Of course, this is also according to one of their own preferences to adjust. Change 1.5 can also be a little bit on the line. Okay, then let's go with 2. Now, we can adjust our lens a little closer so that we can see more clearly. Look, our particles become thinner at the top. When they first come out, they are a normal color and a normal thickness. Go on. Besides adjusting its thickness as we just saw, what other attributes can we adjust? Color, right? We only have black and white color now. It's boring, isn't it? What can we do? We can add a new attribute to it in the middle, that is color. We will see that if we click the middle mouse button, there are many attributes contained in our operator. Let's see, there are 14 attributes here, right? But there is no color in it, so we can add a new attribute. We're going to press the right mouse button in front of the trail to create a lookup texture. That is to say, we can add a color to it through this, okay. So if we want color, we need to create a ramp, create a top, and the ramp in it is an operator of color. Let's pick a random color first. Pick one at random, and then we create a null. And we drag it up to this top. Which means, what are we doing here? We need to tell each particle that the color of each point they correspond to is based on this null 4. So why hasn't it changed yet? Because we haven't given it an output yet. Okay, we can call it output attribute scope here. That is to say, we output a new attribute, right? We call it color here. We can see that we have given the color to it, right? But what is the change of its color now? It changes according to the location, right? We can see that the left side is white, the middle is yellow, and then it becomes white, right? But what do we want to do? For example, we can hope that the color can change according to the growth cycle of the particle, right? For example, we don't need this light now, we can change this P0 here on the right. You see, when we delete both of these, it is equivalent to having no reference, it is a pure yellow. Why did it have this color change when it was there just now? Because P0 and P1 represent our location information, let's change it to something else. For example, let's change it to the particle normal life we just calculated. We can see how our color is. It is white at the top and yellow at the bottom, right? That is to say, at the beginning, it was based on the yellow color on the far left and then slowly turned into a white color as it moved to the right. We can make it more prominent, for example, by changing it to red. Then we can see that the bottom is yellow and the top is red, which is adjusted according to the U and V values. This is a flame-like color, right? Okay, then I might choose the white color we just had as our color here. And then maybe make it a little bit lighter. Okay, what else can we do? We can make it more colorful. For example, in the end, minimize its transparency and we can see it more obviously, right? When it gets to the top, it slowly turns into a transparent color. Okay, for example, at the beginning, let's not make it this color, let's make it a slightly darker red, a slightly darker red. Okay, maybe this is good. I can make this particle feel a little less, make it 200. Okay, now let's adjust our lens again so that we can see more clearly. Okay, so through the many cases we just mentioned to you, we actually want to explain to you that one of the important points in the use of our pop operator is to perform some operations on its properties. And then we can do many of these editing methods, right? Well, we can also add something new and interesting. For example, we can add a small ball like in our case. Let's create a sphere first. Then let's turn down the sphere first, change it to 0.03. Let's change the frequency to a 4 instead of taking up our computer resources so much. Then let's create a copy after it. Actually, if you have used this copy in SOP, you should know that its effect is similar to that of our instance. The effect here is not much different from that of this instance. Then we input the null 3 we just received into the second input port of copy. We can see that our ball has been assigned to the position of this particle, right? Then we create a geo later and render it. We have realized a change of these small balls here. Okay, we can make our ball a little bit smaller. Okay, but now when we look at this little ball, there's a little bit that's not good about it, which is that it suddenly appears and disappears, right? So what else can we do based on the knowledge we just learned? We can make this ball very small at the beginning and gradually increase in size. When it is about to disappear, it gradually fades away instead of appearing suddenly like it does now and then disappearing suddenly in the end. In that case, it's boring, isn't it? We still used this particle normal life parameter here just now to control it. Here, we can create a lookup channel after noise. Through it, we can through a chop. We create a pattern chop here, then we drag it up. Okay, we can make some attributes in this component change according to our pattern, which is a numerical value on top of it. For example, if we look at it here, the default value here is a value that rises from 0 to 1, then changes to -1 and then to 0. We can use it to control the size of the ball we just had. For example, we can make it 0 at the beginning, then 1 in the middle, and finally return to 0, which is the effect we just mentioned, right? So we're here to adjust it. Sometimes we just need to cut it in half, right? We only need the left half of it, the part that changes from 0 to 1, so we changed its phase to 0.25. It is now a data change like what we just mentioned, isn't it? Okay, then let's take a look here and change the lookup attribute to the particle normal life we just created. That is to say, let our control be based on this. That is to say, we control the entire growth cycle of this particle. Finally, what we want it to output is a scale. That is the size. The output is size. Okay, but we don't see any changes, do we? We're here to copy because we didn't apply the scale attribute, right? Okay, let's go inside and find the template. Then we'll open the scale. Then we changed it to the one we just set up called scale. Okay, we have adjusted it, but what have we found now? It's still not quite right, right? It suddenly disappeared, and then suddenly appeared again. Why is this? Let's take a look here. There's a problem with our range, right? We see it as a change from -1 to 1 and then back to -1, right? So it's like the entire data is not quite correct, so let's just make some changes here from range and to range. We changed it from -11 to 01. Now we are a change from 0 to 1, right? Let's take a look now. These small particles are quite right. Okay, and then like what we just learned, how do we give it color, right? Here, we can also give color to these small particles in the same way. It is through this lookup text method that we can create a lookup text in between. Of course, this can be customized according to one's own preferences. I think white is actually quite attractive now. But in order for everyone to review more of the knowledge we just learned, we can adjust the color of these balls by copying these two. Then we use it as our new texture. We drag it up and change the color to better distinguish it. Okay, drag it up. So now let's add a new color to it, right? Okay, don't forget we need to make some changes here, right? Let's first change this to the particle Normalizing we just set up. And then we'll change it to output color. Okay, let's see that now our particles are changing according to our color, right? Why is there no color now? We look at it because after we threw the copy here, it only has 2 positions and there are not many of these attributes, right? So we need to create a new attribute here. We click the plus sign here. We need to turn this on first, and then without clicking the plus sign, we can have it directly. Then we can select it and enter the color. We can see that it gives us the color we just gave, right? Of course, I may still want to keep its white here, so I won't add it. Well, turn it off. Okay, so now we have completed the whole study. That is, how to control attribute.it is the attribute of each particle to achieve the effect in our current picture, right? For example, we use the math mix here to calculate the life cycle of each particle, then control another attribute. Then control another attribute, which is line width, a width of the line. Then we added new attributes such as color inside. Then we also use this lookup channel to control the size of each small particle with this top. For example, as we just saw, we taught everyone at the beginning how to add some new data to a new point cloud file to control this data. We are using data to control its orientation here. Okay, then let me teach you how to add some interactions here. For example, we can add a facial recognition interaction through the media pipe. For example, we can use Arduino to add a brainwave sensor that detects the concentration of our brain and controls the emission of a particle within it. Okay, let's start with this part now.